Hello friends, myself Dr. Nandakumar Raubale from College of Engineering Ambazugai is going to deal with Applied Thermodynamics 2. This is our 9th lecture. In previous lecture, we have discussed numerical on vapor compression refrigeration. So today also we are going to discuss few more numericals on vapor compression refrigeration system. So this is one of the numerical where a vapor compression refrigeration uses methyl chloride. This is the name of refrigerant, which is represented by R40 as a refrigerant and operates between pressure limits of 177.4 kilopascal and 967.5 kilopascal. So 100 kilopascal is equal to 1 bar. So here this is the pressure range. The compression is isentropic. So again here process of compression is isentropic. The vapor is in dry saturated condition at the beginning of compression. So when this enters into the compressor refrigerant, it is dry saturated. That is nothing but it falls on this dry saturation curve, and where pressure P1 is 177.5 kilopascal and upper pressure is 967.5 kilopascal. Then the process of compression is isentropic, which is represented by vertical line on TS diagram. So this vertical line 1 to 2 represents isentropic compression, and at the starting of compression, the refrigerant vapor is dry saturated, which is represented on this saturation curve. Now after compression it reaches to 102 degrees Celsius. So temperature of a refrigerant at point 2 is 102 degrees Celsius. The temperature of a liquid refrigerant as it leaves the condenser is 35 degrees Celsius. So saturation temperature at 967.5 kilopascal, which is given, is 45 degrees Celsius. But when this condensation process starts from point 2 to 2 dash, then it comes to 3 dash. So actually when it becomes a liquid, saturated liquid, we expect that it is passed into the throttling valve. So instead of passing it as soon as it becomes saturated liquid, it is undercooled. So here there is undercool of refrigerant from 3 dash to 3, and which is 35 degrees. So temperature at this is 35 degree at 3, and temperature at 3 dash is 45 degree. So difference between these two is known as undercooling. So the refrigerant, as it gets condensed into the liquid state, soon it is not passed into the throttling valve, then again it is subcooled, and then afterwards it is passed into the expansion valve. So this subcooling is of 10 degrees Celsius. Then specific heat carrying capacity, that is CP, of refrigerant is 1.624 kilojoules per kg Kelvin. Estimate theoretical coefficient of performance. So he is asking us to find out COP of the refrigeration system. So now what is given here? Pressure P1 or pressure P4, one and the same, it is 177.4 kilopascal. So this is given. Then second highest pressure is given, that is 967. This is 967.5 kilopascal. Then he is saying that at the starting of compression the vapor is dry saturated. So refrigerant is dry saturated, dryness fraction is 1 at 0.1. So this compression process is isentropic, and at the end of compression he has given one more data, that at the end of compression the refrigerant reaches to 102 degrees Celsius. So refrigerant becomes the temperature at point 2, that is T2, is 102 degrees Celsius. This is also given, and the temperature of refrigerant at point 3, T3, which is given as 35 degrees Celsius. So temperature at point 3 is 35 degrees Celsius, which is given in the problem. So here the refrigerant when it leaves the condenser is 35 degrees Celsius. So that is nothing but As soon as it becomes a saturated liquid, it is not leaving the condenser, it is still cooled below this temperature of saturation up to 3.3, means temperature at point 3 is 35 degrees Celsius. Then he is asking us to find out coefficient of performance. So to find out coefficient of performance, as usual, so COP is defined as refrigerating effect divided by work done. So refrigerating effect is given by H1 minus H4. So enthalpy at point 1 minus enthalpy at 4. So refrigerating effect starts at point 4 and it continues up to point 1. Then work done starts at point 1, ends at point 2. Work done is H2 minus H1. So what we have to find out is H1, enthalpy at point 1. So enthalpy at point 1 can be given as HF1 plus of X1 HFG1 at pressure P1 bar or P1 kilopascal. So here X1 is given as 1. So dryness fraction is given as 1. So from this H1 can be obtained. So to find out H2, enthalpy at point 2 can be obtained as HF2 plus of HFG2 plus of Cp into T2 minus of T2 dash. So enthalpy of dry saturated steam at point 2 dash plus of enthalpy of superheated steam, that is Cp into T2 dash T2 minus T2 dash. So T2 minus T2 dash at pressure P2 kilopascal. So this is also at pressure P2 is equal to whatever is given in this problem. Then we must know enthalpy at point 4. So enthalpy at point 4 is equal to enthalpy at point 3, because this 3-4 process is throttling process. There what we say, enthalpy before throttling is equal to enthalpy after throttling. So enthalpy at point 4 is equal to enthalpy at point 3. So enthalpy at point 3 can be known as HF3. So enthalpy at point 3 is HF3. We don't know pressure at this point, only we know temperature. So from this temperature we can find out this drop, enthalpy drop. HF3 we know. HF3 we know. From this HF3 minus of Cp into T3 dash minus T3. So actually HF3 can be taken from steam table, or else this H3 can directly be obtained from steam table. But what happens here? So to know H3 we must know pressure at point 3. So third pressure P3 is not known. But if we take this 35 degrees Celsius as saturation temperature of liquid, from that also we can take H3 directly from vapor table or refrigerant properties table. But here in this problem, only at two pressures or at only two temperatures this property table is given. But if you know, if you have the property table of R40 refrigerant, then you can take the condition HF at 35 degrees Celsius. So that will give you directly HF3. So HF3 can be obtained in this case from subtracting HF3 dash minus of Cp into T3 dash minus T3, or directly HF3 can be obtained from steam table at temperature of 35 degrees Celsius. Only condition provided that if you have the property table for refrigerant R40, then only it is possible. So now we will start to solve this. So H1, enthalpy at point 1, that is H1 is equal to HF1 plus of X1 HFG1 at pressure P is equal to here data taken is something wrong. So this data we won't refer. This is the wrong table. So now this is at pressure P is equal to lower pressure, that is 177.4 kilopascal. So now from this table we can take HF as 45.38 kilojoules per kg, 45.38 plus x1 dryness fraction value which is given in this problem is 1. So this is 1. So we can take it as 1. 1 into HFG1 is 415.38. So this gives us enthalpy at point 1 at the inlet of compressor, 45.38 plus 415.38. So this is 460.76 kilojoules per kg. So enthalpy at point 1 is known. So to find out enthalpy at point 2, enthalpy at point 2 or state 2, that is nothing but H2 is equal to, we can say that as HF2 plus of HFG2 plus of Cp into T2 minus of T2 dash. So it can be taken in degree Celsius or in degree Kelvin, it makes no difference. So HF2 at point 2 is 132.98 plus of HFG2 is 350.62 plus of Cp, specific heat which is given in this problem, is 1.624 into T2, temperature at point 2 is 102 degrees Celsius which is given in the problem, and T2 dash, temperature at point 2 dash, is taken from this property table, so that is 45 degrees Celsius. So this is at pressure P2. Saturation temperature is 45 degrees Celsius, that is minus 45. So then we get this as 102 minus 45 into 1.624 plus of 350.62 plus of 132.98. So this is 576.16 kilojoules per kg. This is enthalpy at point 2. So enthalpy at point 3, enthalpy at point 3 dash, we call this as at point 3 dash. So that is nothing but HF3 dash is given from the steam table. HF3 dash at point 3 pressure is P2. So HF3 dash is 132.98 kilojoules per kg. Now to know enthalpy at point 3, H3 is equal to HF3 dash minus of Cp into T3 dash minus of T3. So HF3 dash we know that is 132.98 minus of Cp is 1.624 into T3 dash. T3 dash which is given here is 45 degrees Celsius at pressure P2. Saturation temperature is 45. So 45 minus of T3 which is given in problem is 35. So this gives us 132.98 minus of 1.624 into 10. This is 116.74 kilojoules per kg. 116.74 0.74 kilojoules per kg is the enthalpy at point 3. So from this we know H3 means H3 is equal to H4. So we know H1, we know H2, and we know H4. So from that, refrigerating effect can be obtained. That is nothing but H1 minus H4. So we know value of H1 is 460.76. 460.76, and H4 just now we calculated as 116.74. 116.74. So this gives us a refrigerating effect as 460.76 minus 116.74. So this is 344.02 kilojoules per kg. So this is a refrigerating effect. Then work done in compressor is given by H2 minus H1. So here we know enthalpy at point H2, we know enthalpy at point 1. So H2 minus H1. So H2 is 576.16. 576.16 minus of H1 is 460.76, which is equal to 576.16 minus 460.76. This gives 115.4 kilojoules per kg. So COP of system is equal to refrigerating effect divided by work done. So refrigerating effect is 344.02 and work done is 115.4. So COP we get as 344.02 divided by 115.4. This is 2.98. 2.98 is the COP. So summary of this is, we know H1 value, which is equal to 460.76 kilojoules per kg. We know H2, that is 576.16 kilojoules per kg. Then we know H4, which is 116.74 kilojoules per kg. Then refrigerating effect is 344.02 kilojoules per kg. Work done is equal to 115.4 kilojoules per kg, and COP, coefficient of performance, is 2.98. This is summary of this problem. So now we will proceed to the next problem. We proceed to the next problem in this case. Okay, the next problem is given like this. So here this considers superheating in a evaporator and undercooling in a condenser. So the vapor compression refrigeration plant uses Freon 12 as a refrigerant, has a capacity of 12 ton. So refrigerating effect in tons is 12 ton of refrigeration operating between minus 28 to 26 degrees Celsius. So this temperature is minus 28 and this temperature is 26 degrees Celsius. the refrigerant is subcooled by 4 degrees. So from T3 dash, so temperature from 3 dash to 3 is 4 degrees Celsius before entering into the expansion valve, and vapor is superheated by 5 degrees Celsius before leaving the evaporator. Means, so here this vapor is superheated by 5 degrees Celsius. Here 5 degrees Celsius is the superheating, and here subcooling is 4 degrees Celsius before leaving the evaporator. Determine coefficient of performance and mass flow rate of refrigerant. So here temperature at point 1 is 1 dash is minus 28 degrees Celsius, and temperature at 2 dash, so temperature between 3 dash and 2 dash is 26 degrees Celsius, whereas the temperature difference between T3 dash and T3, so this temperature difference T3 and T3 dash is 4 degrees Celsius, and temperature difference here the superheating is 5 degrees Celsius, means T1 minus T1 dash is 5 degrees Celsius. So when the refrigerant enters into the evaporator, it absorbs latent heat and again it absorbs sensible heat. It becomes superheated when it enters into the compressor. So superheated vapor enters into the compressor and it gets compressed. So here the temperature at point 2 we don't know. However, we know this temperature difference. So now he is asking us to find out coefficient of performance of a refrigeration system and mass flow rate of refrigerant. So then what we have to do is coefficient of performance is equal to refrigerating effect divided by work done. Again similar formula we have to use, that refrigerating effect in kilojoules per kg is H1 minus H4. So if we know enthalpy at point 1 and enthalpy at point 4, we get refrigerating effect. Then work done is from point 2 to 1 to 2. So H2 minus H1 is work done. So to how to find out H1, enthalpy at point 1 is nothing but HF1 plus HFG 1 plus of Cp into T1 minus of T1 dash. So this temperature difference is given to us, and Cp which is to be taken in this problem is not given, I think, even though we'll see what is actually given or not. It may be given. Vapor, that is 0.615. So Cp is given 0.615 kilojoules per kg Kelvin. So in previous problem Cp was assumed constant, and one value whatever is given it is for superheated steam and wet steam. But in this case this is the value for specific heat of a refrigerant when it is superheated, and specific heat of liquid refrigerant, Cp of steam and Cp of liquid, which is given as 0.963 kilojoules per kg degree Kelvin. So this is also given. So specific heat at constant pressure of vapor and specific heat of liquid, both are given. Now to find out this COP and all, that we will see. So Cp is given, Cps is given, Cpl is given. So Cps is 0.615 kilojoules per kg Kelvin, and Cpl is 0.963 kilojoules per kg Kelvin. So now H2 can be obtained. So here HP steam and SPL we take here. So H2 enthalpy at point 2. So Cp it is same. So Cps only. Here Cpl will be there. So H2 is equal to HF2 plus HFG2. H2 is equal to HF2 plus HFG2. T2 minus of T2 dash. So here we know T2 and T2 dash difference. We know this difference. We don't know, I think. This superheating we know, but this we don't know. So for that we have to find out temperature of superheated steam. T2 has to be obtained. Then H4 is equal to H3 and H3 is equal to HF3 minus of CPL T3 dash minus T3. Then HF3 dash can be obtained as HF at point pressure P2. So at pressure P2 we can take this as 60.67. So now we'll proceed to find this one by one. So to find out enthalpy at point 1, H1 can be given as HF1 plus of HFG1 plus of CP into T1 minus T1 dash. So HF at pressure, this is taken at pressure P1 is equal to 1.093 bar, or saturation temperature at minus 28 degrees Celsius. So this is working between temperature limits of minus 28 to 26 degrees Celsius. So here HF1 is taken as 10.64. So 10.64 plus HFG is 164.47. 164.47 plus of CP of steam, which is given as 0.615 into T1 minus T1 dash, which is given in this problem as 5 degrees Celsius. I think it is T1 minus of T1 dash is 5 degrees Celsius. So this is taken as 5. So altogether is 5 degrees Celsius. So now from this we can find out H1. So 0.615 into 5 plus of 10.64 plus of 164.47. So this gives us 178.18 kilojoules per kg Kelvin. So we know H1, so enthalpy at point 1. To know enthalpy at point 2, we must know temperature at point 2, or temperature difference between T2 dash and T2. So to find out this condition of temperature at point 2, we have to equate entropy at point 1 is equal to entropy at point 2. So entropy at point 1 can be written as SF1 plus of SFG1 plus of CP natural log T1 divided by T1 dash, which is equal to SF2 plus of SFG2 plus of CP natural log T2 divided by T2 dash. So this is at pressure P1 and this is at pressure P2. So we know SF1 from this steam table. At pressure P1, SF1 is 0.00444. So 0.0444 plus of SFG is 0.6709 from steam table plus of CP is 0.615 natural log T1 temperature 1 divided by temperature 2. So temperature 1 is known to us, that is T1 dash. T1 dash which is given in this problem at lower temperature. So this is minus 28 degrees Celsius. Minus 28 degrees Celsius plus of 273. In the numerator we can take this T1 as 5 degree difference. So minus 280 minus 28 means this will be plus 5 minus 23 minus 23 plus of 273, which is equal to SF2. SF2 it is at pressure P2, which is given as 0.2271 plus of SFG2 is 0.4594 plus of Cp is 0.615 natural log. T2 we don't know, that we want to find out. T2 dash we can find out. T2 dash is 26. So temperature at saturation temperature at pressure P2, which is 26 degrees Celsius, means 26 plus of 273. So we simplify this left hand side and we will write its answer, and then we simplify on right hand side what we get. So here 0.615 into natural log of bracket double bracket minus 23 plus of 273 bracket close divided by another bracket minus 28 plus 273 bracket close this bracket plus of 0.6709 plus of 0.0444, which is on left hand side we get this as 0.7277. On right hand side if we add these two, 0.2271 plus of 0.4594, we get this as 0.6865 plus of 0.615 natural log T2 divided by 26 plus 273 gives us 299 degree Kelvin. So this can be simplified. 0.7277 minus 0.6865 divided by 0.615 inverse natural log gives us, this is 1.06 into 299. So this is T2. We get on simplification T2 is equal to 319.71 degree Kelvin, or in degree Celsius minus 273, which gives us 46.71 degree Celsius. So temperature in degree Kelvin is 319 and in degree Celsius 46. So now to find out H2, enthalpy at point 2, so H2 is equal to, we can write it as HF2 plus of HFG2 plus of CP T2 minus of T2 dash. Now HF2 can be taken at pressure or temperature 26, this is 60.67 plus of HFG2 is 137.44 plus of CP is 0.615 into T2, just now we calculated in degree Celsius as 46.71 minus of T2 dash. T2 dash here given is in this problem is 26 degrees Celsius. Saturation temperature at this pressure is 26 degrees Celsius. This is minus 26. So we get H2 as 46.71 minus 26 into 0.615 plus 137.44 plus 60.67. This is 210.84 kilojoules per kg. So this is H2. Now to find out H3, which is equal to H3 dash minus of Cp T3 dash minus T3. So in this problem, subcooling is given. I think subcooling is 4 degrees Celsius. So 4 degrees Celsius is subcooling. So therefore, how much is subcooling here? 4 degrees Celsius. So this temperature difference is 4 degrees Celsius. So H3 dash at this temperature or pressure, temperature of 26 degrees Celsius, H3 dash is nothing but 26 degrees Celsius. It is 60.67. So this is 60.67 minus of Cp is 0.963. So this is Cp liquid. So this is liquid line. So therefore we take here Cpl. Here we take Cp. Yes. Here we take Cp. Yes. So liquid we take it as, and then this temperature difference which is 4 degrees Celsius. So we get H3 as 60.67 minus of 0.963 into 4, which is equal to 56.81 kilojoules per kg. So H3 is nothing but H4. H4 is equal to H3, and H3 is equal to H3 dash minus CPL, T3 dash minus T3. So this is given in the problem. CPL is also given in the problem. So we get this as H3. So now from this we can find out refrigerating effect as H1 minus of H4. So H1, which we have calculated here as 178.18 minus of H4, or H4 is equal to H3, which is 56.81 kilojoules per kg. So this is refrigerating effect 178.18 minus of 56.81. This is 121.37 kilojoules per kg. Then work done, which is nothing but H2 minus H1. So H2 value we know, that is 210.84 minus H1 value we know, that is 178.18. So 210.84 minus 178.18. So this is 32.66 kilojoules per kg. So this is second thing. Then COP is obtained as refrigerating effect divided by work done. So refrigerating effect is 121.37 kilojoules per kg divided by work done is 32.84. So here therefore 121.37 divided by 32.84 gives us 3.69 as COP. So now one more thing is asked in this problem, is that he is asking us to find out mass flow rate of a refrigerant. So to find out mass flow rate of refrigerant, so what is given in this problem and what has to be done, that we will see. So refrigerating effect which we have obtained here is what we say is refrigerating effect is 121.37. So refrigerating effect is 121.37 kilojoules per kg. So now once we know refrigerating effect, then he has given refrigeration capacity, that is heat carrying capacity Q, in kilojoules per minute in this problem is in terms of refrigeration. So 12 tons, 12 ton of refrigeration. So 12 ton into 210, then it gets converted into kilojoules per minute. 12 into 210, 2520 kilojoules per minute. So if we divide refrigerating effect divided by this capacity, then we get if we divide this capacity by refrigerating effect, we get the mass flow rate of refrigerant. So mass flow rate of refrigerant MR is given by Q divided by refrigerating effect. So Q is 2520 divided by refrigerating effect is 121.37. So this is in kilojoules per minute and this is in kilojoules per kg. Kilojoules gets cancelled. Kg, which is in the denominator of denominator, goes into numerator and unit will be kg per minute. So this is 2520 divided by 121.37. So this is mass flow rate is 20.76 kg per minute. So mass flow rate of refrigerant we get as 20.76 kilojoules per kg. So in short, we will write its summary. So enthalpy H1, then we find out enthalpy H2, then we find out enthalpy H4, then refrigerating effect, then work done, and then COP and mass flow rate of refrigerant. So H1 value which we obtained here is 178.18 kilojoules per kg. Then we obtained value of H2 as 210.84 kilojoules per kg. Then H4 we obtained as H4 56.81 kilojoules per kg. Then refrigerating effect we obtained as 121.37 kilojoules per kg. Then work done we obtained as work done is 32.66 kilojoules per kg. COP we obtained here as 3.69 and mass flow rate of refrigerant 20.76 kg per minute. So this is how we obtained the solution for the second problem, in which we have seen as two things, that is there is superheating before entering into the compressor, then at the end of compression superheated steam, and again subcooling. So three things are combined in this problem. So only thing is to find out T2. We have to equate S1 S2 is equal to S1, then we find out temperature T2, and once we find out temperature T2 we can find out enthalpy at point 2. So this temperature at point 2 dash, which can be obtained from pressure, that is at 26 degrees Celsius is saturation temperature here, and here it is minus 28 is saturation temperature. So this is to be remembered. And one thing in this problem, when we find out this entropy, so temperature in the numerator in this natural log, in denominator here temperatures must be in, very important thing is these temperatures must be in degree Kelvin. If these are kept in degree Celsius, then the answers will go wrong. So but here we can substitute both in degree Celsius or both in degree Kelvin. To find out enthalpy of superheated steam, the temperature values can be substituted here as in degree Celsius or in degree Kelvin, both in the same unit. So this is the major thing that one has to take into account while finding this. So here we stop.